Welcome back to Silicon Scoop, everyone. With me, as always, is my co-host John Irwin. How you doing this September 2nd, John?
Good. How are you?
I'm doing fantastic and ready to get back into the swing of things of work.
Okay.
I had so many meetings I scheduled last week canceled just because people are away, and it's like I should have known better, but I tried.
Yeah.
But let's jump into this. We got a lot to talk about today, and we're back talking about quantum. Today, it's a genuine breakthrough where Japanese researchers use quantum entanglement to make robots move smoother, smarter, more precisely, cutting posture error up to 43% with a hybrid quantum classical controller. Let's talk about what this thing is, why it matters, when it's coming. What's going on here, John?
Yeah. So they use quantum computers to make. So this is robots in quantum, right? So it makes robots move more smoothly and accuracy. If you think about it like they're upgrading the robot's brain from a regular calculator to a supercomputer. And so the problem that they solved was, so when robots need to move their arms or bodies, they face what's called the inverse kinematics problem. So it's like asking, if I want my robot's hand to touch this specific spot, what angle should each joint be at? So for complex robots with many joints, like humans have 17 joints in that, for them to get to that, it becomes really, really difficult to calculate quickly and accurately. So the breakthrough that they figured out how to represent each robot's joint as a qubit and use quantum entanglement, where quantum particles, you'll love this word, mysteriously influence each other to mirror how real robot joints naturally affect each other when they move. So this reduced calculation errors by up to 43% while using fewer computational steps. So why does this matter? Because it could lead to robots that move more like humans. So fluid response, responsive, and able to handle complex tasks in real time without that jerky, simplified movements that we see today. So my thoughts, Craig, I didn't know that it was the lack of computational power. I thought it was the lack of the actual muscles and things like that that made them jerky and whatnot. What are your thoughts on this?
Yeah, once reading into this, it was pretty enlightening. You know, a humanoid robot with 17 joints creates an incredibly complex calculation problem that, they're having a hard time understanding. You're walking, and if your arm's so far forward, what does that do to your balance? And you got to calculate all this stuff, the things that we do automatically. So apparently that it becomes computationally challenging, and that's what's causing this herky-jerky motion.
Yeah, which I didn't think it had anything to do with the actual motors and stuff. I thought it was more the lack of muscles for that fluid movement, if that makes sense. So if that's the case, then although remember that video that we saw with the muscle and the robot jerking and stuff like that?
Yeah.
Yeah, this is interesting. It kind of blew my mind when I read into it a little bit more.
Yeah, that a robot freaking out when it was on a thing, we have no idea what was going on there. So it's hard to judge that because it could have been trying to find its balance. Like it's used to standing up.
Yeah.
And now it's hanging on something. You turned it on and tell it the balance, and it's trying to figure out, and then it glitches out and gets an error and starts, doing whatever. It's not what it looks like is it's trying to kill somebody versus it, a natural computational issue. To me, I mean, quantum seems like a leap to solve how smooth a robot walks and can pour drinks and stuff like that. So
yeah,
we've seen the robot marathon. We've seen a bunch of things. I guess what this allows is robots to sync in unison as well, more to know exactly where the other one is and that kind of stuff at a computational level so they don't interfere with each other in a close environment. And I guess the qubit-based representation fundamentally changes how robots process movement calculation. So instead of calculating each joint independently and then combining them, quantum systems can process interconnected joint relationships simultaneously. So the quantum, so like when it naturally affects the elbow and the wrist. So for example, when a shoulder joint moves, it naturally affects the elbow and the wrist. And quantum entanglement can represent these relationships more efficiently. So it's great if we have quantum computing working and whatnot, and a 43% in posture errors versus conventional methods. And I don't know, does that seem like a big leap to you?
I would think so, because like you're converging two transformative technologies here, right? So this is all like, so the research indicates that quantum algorithms could address multiple robotic challenges, not just the movement, but path planning, sensor data processing, like you said, multi-robot coordination, and decision making under uncertainty, which is interesting. So again, we don't fully understand quantum, and we kind of do, but we don't. And you and I have covered quite a bit. But the cool thing about this approach is that this might seem ridiculous to people, but the quantum approach, it only requires 1 qubit per robot link. So it makes it feasible for we talked about this before, but the noisy intermediate scale quantum, which is the NISQ devices. And so a humanoid robot with 16 links would only need 16 qubits. And that is kind of well within our current hardware constraints that we have, right? So like we talked about a couple times, the quantum entangled circuits demonstrated up to 43% error reduction compared to non-entangled approaches. So this suggests that the methods could enable, like we talked about, real-time robot control for complex multi-joint systems. So it's more of a representation of how human neural networks control complex movements, which is going to help us in the future. But yeah, I'm still curious as to how they've implemented quantum entanglement with these robots to use it for their movements, right? Because it doesn't dive into like the real nitty gritty.
Well, quantum entanglement mechanism works by creating qubits that represent joint position. So because standard computing is binary, it's on or off, qubits can represent things at a mere final level. They can represent multi-states of being. So a qubit that represents joint positions or rotation as interconnected quantum states. When a parent joint moves, the entangled qubits automatically reflect this movement in the child joints throughout the system. This quantum representation processes complex joint relationships simultaneously rather than sequentially, which is great. But I guess your question is, how are they physically implementing this into the?
Yeah, we know the theory behind it, right? That that it represents points in a 3D space. The qubits can naturally represent points in a 3D space through their state vectors. The forward kinematic calculations are performed using quantum circuits, and each qubit encodes the posture of its corresponding robot link. And each position calculations involve measuring the expected values of the qubits with respect to the XYZ rotation gates, and then multiplying by the physical link lengths. But I'm curious as to, yeah, you're right. How are they physically doing this?
Yeah, and I commented on the 43% error rate reduction doesn't sound like much, but I guess without a base saying it's 90% accurate, now we're going 43% more accurate or what have you. We don't, understand what we're moving there, because if we say 43% more accurate, it sounds like we still have a long way to go rather than we're really honing in on the last 10, 20%, which takes the hardest, right?
Yeah.
And, thinking about it, things like this will allow potentially things like remote surgery, where things will have a extreme fine movement with robotics and stuff versus, any delay or herky-jerky motion when you're talking about that kind of stuff would ruin the potential outcome.
Yeah. And my question is, where is AI in all of this?
Yeah, I guess that is a very good question. I guess the problem is AI is computational. So
yeah,
if you feed it all this stuff, it's still trying to figure it out. So I don't know if that will make any sense.
Yeah, I'm guessing that they're using AI or in their research and as they're developing this. I was curious that as to like when we talk quantum, we don't really talk AI. We have a couple times, but we haven't talked AI when it comes to quantum too much.
Yeah, okay, let me separate this. So I think AI is involved in all this. AI is telling the robot how to move, where to move, and doing the calculations and saying, okay, I'm gonna you're gotta go over there. There's stuff in the way, so I've got to walk around these three things, and then I don't know how fragile it is, so I have to check the tensile, whatever. That's AI, but the actual bot moving will have to be reflected at the quantum level, right? And you would assume that the AI would say, move forward 10 feet. It wouldn't say, move 1 foot forward 6 inches, lift it up, put it down, blah, blah, blah. They would hand it off to a system that understands the movement because, as we all know, AI is slow. So we want AI to do the stuff that is required to do that. And anything you can do in code or something else, it's just like, okay, you want me to move 10 steps? Great. And we'll just have the AI detecting if there's a problem, if I need to stop or if I need, alerts and that kind of stuff.
Yeah.
So I like this concept, but we don't know. There's no pricing yet. Early access likely via cloud simulators and hardware partnerships, and enterprise R&D pilots will be bundled with software. This is fresh research as of August 25th, 2025. We're validated on similar and 64 qubit hardware. No commercial timeline yet for any of this stuff. So
yeah,
very interested.
What I read was, I think, 5 to 10 years, but again, that's typical. So a typical timeline that we talk about, right?
Yeah. So 5 to 10 years for what? Quantum in robots, or 5 to 10 years for us to have regular robots running around? Like, we have robots.
So experts are suggesting 5 to 10 years for practical quantum robotics applications emerging.
Yeah, and it looks like the answer is going to be a hybrid of the quantum and traditional systems to make everything work together properly. So I'd love to hear what you think on this. Quantum won't replace classical control. It looks like it's going to augment it where relationships matter most. The next wave of robots won't just compute faster. They'll move faster. They'll move better. So stay tuned. As pilots roll from labs to factories, hospitals, and homes, we'll be there to cover it. Thanks for listening and watching. What do you got going on, John?
Oh, just working away, helping companies secure government funding. Maybe heading to a couple events. I'm not sure what's coming up. So this will probably come out after Elevate.
Yeah.
So Elevate probably would have been a great time. But yeah, how about you, Craig? What do you have?
So assuming this is November, we got a Flowgrammer event and a Toronto Startup Investor Drinks. If you're in the GTA area and want to learn or be part of a Flowgrammer, N8N, or Vibe Coding meetup group, join us. Go to flowgrammer.ca and check out the upcoming events and join us. If you want to find out more about how to take your startup to the next level, head over to torontostarts.com. Our events there, Startup Investor Drinks. So we do monthly. It's open bar, open pitch. It's an intimate event, and the conversations are next level. So check all that out there, and we'll see you in the future. Anything else, John?
No, that's it.
So thanks, everyone, for listening. Don't forget to like and subscribe and leave a comment. We really appreciate it. Have a great one.